All right, welcome. In this explainer, we are diving into a topic that is literally all around you, from the deepest oceans all the way to the air you're breathing this very second. We're talking pressure in fluids, a super important part of your GCSE Physics course. So, let's get right into it.
So, to get our brains warmed up, think about this for a second. Why is it so much easier to cut something with a really sharp knife compared to a dull one? I mean, you're pushing with the same amount of effort, right? Well, the answer is all about pressure. And by the end of this, you'll see exactly why.
Okay, so to get to the bottom of our knife question, we have to start with the absolute basics of what pressure actually is. Let's build this whole thing up from the ground floor.
First things first, we need to get a key term straight in our heads: fluid. Now, in everyday life, we think of fluids as just liquids. But in physics, a fluid is anything that can flow. And that means it includes both liquids and gases. This is a really crucial point for everything that follows.
And this right here is the answer to our knife question. See, pressure is all about how concentrated a force is. A sharp knife takes all the force you're applying and focuses it onto a tiny, tiny point. A dull knife spreads that exact same force over a much bigger area. So the key takeaway is this: same force, smaller area, way, way more pressure.
And you know, in physics, if there's a concept, there's an equation for it. Pressure, or P, equals force F divided by area A. Now, getting the units right here is absolutely critical in an exam. Pressure is measured in pascals, force is in newtons, and the area must be in meters squared. Be super careful if a question tries to trip you up with centimeters.
Okay, exam alert. This is a big one. This equation, P equals F over A, is not given to you on the physics equation sheet. You've got to know it by heart. Seriously, drill this one into your memory. You will need to recall it.
Right, now that we've nailed the basics, let's dive a little deeper, see what I did there, into how pressure works specifically in liquids.
You've all felt this, right? You're in a swimming pool, you swim down towards the bottom, and you can feel the pressure building up in your ears. Well, why is that? It's because you have the entire weight of the column of water directly above your head pushing down on you. The more water there is above you, the more weight, and therefore, the more pressure. It's that simple.
And of course, there's an equation for this too. The pressure in a liquid equals H times rho times G. Let's quickly break that down. H is the height of the column of liquid, or basically the depth. That rho is a Greek letter, rho, and it just stands for the density of the liquid, and G is the gravitational field strength.
Okay, some good news for you on this one. This liquid pressure equation is on your equation sheet, so you don't need to memorize it. But, and this is a big but, you absolutely have to know what each symbol means and how to plug in the right numbers to use it correctly. Don't stress about G, its value will always be given to you in the question.
So, this whole idea that pressure gets bigger the deeper you go. Well, that leads to this really cool effect, an upward force that exists in any fluid. It's called upthrust.
So what exactly is upthrust? Think about trying to push a beach ball underwater at the pool. It's tough, right? And the second you let go, it shoots back up to the surface. That upward push from the water, that's upthrust. It's a force that's always fighting against an object's weight. Okay, so how does it actually work? Let's walk through it. Imagine a can of soda and some water. The bottom of the can is deeper than the top of the can. And since we know pressure increases with depth, the water is pushing up on the bottom with more force than it's pushing down on the top. And that difference creates a net or resultant force pushing upwards. And that, my friends, is upthrust.
When it comes down to it, floating and sinking is just a simple tug of war between two forces. You've got the object's weight, gravity, pulling it down, and you've got upthrust from the fluid pushing it up. If the upthrust wins, the object floats. If the weight wins, the object sinks. It really is that straightforward.
Okay, we've talked a lot about liquids, but let's not forget, gases are fluids too. And right now, every single one of us is living at the bottom of a gigantic ocean of air. We call it the atmosphere, and it's creating pressure on us all the time.
So our atmosphere is this thin blanket of air that's held around the Earth by gravity. It's made of billions and billions of tiny molecules, all whizzing about and constantly bumping into everything, including you. Every single one of those tiny collisions adds up to create what we feel as atmospheric pressure. And here's the key bit. The higher up you go, the thinner or less dense that air gets.
This is exactly why your ears pop when a plane takes off. It's the same principle as a swimming pool, just with air. As you go higher up, there is literally less air above you. A shorter column of air means less weight pushing down. and that means lower atmospheric pressure.
Phew, we have covered a ton of ground, so let's wrap this up with a super quick fire summary. This is the absolute must-know stuff, the bits you really need to have locked in for your exam. All right, here we go. The two big equations you need to know. First, P equals F over A. That's for calculating pressure on a surface, and you must remember it. Second, P equals H rho G. That's for pressure in a liquid column, and that one is given to you on the sheet. You have got to know which is which, one for surfaces, one for liquids, one you memorize, one they give you. Simple as that.
And I'm going to leave you with one last question to chew on. The atmospheric pressure pushing down on you right now is enormous. We're talking over 100,000 pascals. That's like having more than 10 kilograms of weight on every single square centimeter of your skin. So, why doesn't it crush us? The answer uses all the principles we've just covered. Have a think about it. Thanks for joining me for this revision session.